Okay, so the third and last speaker of this session is Nicolas Laflorencie, who will tell us about a new perspective on MBL.
Okay, thank you, Valentina. Thank you, all of you, to be here this last day. Thanks a lot to organizers. It's very great for me to be here, my first time in India. So you see, just bought that yesterday in the city. I think this is my last talk with the Université Paul Sabatier because it will disappear. It will be replaced by University of Toulouse, January 1st. It's a bigger thing. Okay, so this is the title of my talk, so I will try. So this is a bit of the follow-up after Fabien's talk on Monday about basically the same model. And so we will revisit many-body localization using simple objects, which are these spin correlation functions. So this is a joint work with Fabien, of course, and also Jeanne Colbois, who did her postdoc with us in Toulouse in the past 2 years, and now she got a permanent position at CNRS in Grenoble. Okay, so this is the outline of the talk. So I will briefly remind what is the status of the MBL problem nowadays. And then I will introduce this very simple object, the correlation functions, and then discuss deeply this object across the many-body localization phase diagram. And with that, we have discovered that the rare events are very, very important, in fact, and so we are going to discuss them as much as possible. So, MBL in one slide. Thank you, Fabien, of course, because he did a half an hour introduction on that. So if you're interested, there are a few interesting big review articles, and I strongly suggest the last one, which is the most up-to-date, and I think this is a very great work. So if you're new in the field, don't be afraid, and you can go to this review article. There are a lot of very, I think, deep and relevant information. So the basic question, of course, back to old days of MBL, is can Anderson localization survive to interaction? And so one of the first answers, of course, was yes. Okay, good examples in this paper, analytical paper, where they show that indeed putting weak interaction at least make Anderson survive. So an insulator, which is called a many-body localized insulator. But in fact, it's also a no. And this is what we recently found in this paper. It's very small, but this is the paper that Fabien discussed at length, that if along the Anderson line, the non-interacting line, if the disorder is not very strong, that means your bare localization length is quite big, and in that situation, you are in a different side, if you wish, as compared to this avalanche criterion, and it could be that weak interaction immediately delocalize your system. So in fact, there are two possible scenarios. So the answer of this question is yes and no. So that's, I think, an important detail to say. So then, what are the main properties of MBL? So here I give a list. Okay, we can class them in two categories: eigenstate property and out of equilibrium property. So for example, eigenstate, they have very low entanglement. They have a spectral statistic which is Poissonian. If you go to Hilbert space, there is genuine multifractality. Okay, and then if you're interested in out of equilibrium properties, there's no thermalization. This is one of the big thing. And for example, there is a memory of the initial, for example, spin or charge pattern that can remain a very, very long time. And if you're interested in entanglement, the growth is extremely slow, ultra slow, like a log logarithmically growing. And among all these, this is mostly numerical observations. And there are only a few analytical developments. One which is very successful is this LBIT model, where, okay, but for me, it's still a sort of phenomenological model. It explains a lot of things, but I think it doesn't explain all of things, all what we observe. So, of course, on that, there are important debates. And here, I cannot resist to show you this, how the estimate of the critical disorder strength for the Heisenberg chain in a random field has evolved along the years. And so you see, in fact, on that scale, of course, you see it goes from 0 to 20. It's okay. this is reasonable, I would say, within error bars, except a few like outliers. And this one, in fact, this blue big error, well, it's not an error, of course. This is like a range of different estimates. It came from the Morningstar and David Hughes paper, well, Colmenares, Kemani, Luiz, and David Hughes paper, where they, in fact, they described what we think to be the MBL regime on finite system as a sort of a series of landmarks where, depending on what you look at, you think to observe MBL transitions. And important, like, thing they observe is this system-wise resonances, okay, that they think to observe around disorder 7, okay? So I will come back later to these numbers, what they mean in our language. And so they say these are some kind of precursor, finite size, of the dominant mechanism of the transition, which is supposed to be avalanche instability. And what they call the avalanche instability come here. And so this is what they expect to be the infinite size phase diagram. So only 2 phases, an ergodic thermal phase and an MBL phase. And so they say what all we see in numerics is some kind of pre-thermal thing, and at the end of the day, everything that will disappear. Okay, I don't fully agree with that, so you will see why. But okay, this paper was quite influential, and so many people believe okay, MBL maybe does not exist. Also, this I'm not this family, but okay. So. There are many ways of tracking MBL, but something which I think was missing is a true real space object to catch possible system-wide resonances. And to do that, there is like a very simple candidate in real space, which is a 2-point correlation function. Okay, so we are going to go with our favorite model, the XXZ, okay, which is supposed to be a standard model for MBL. So this XXZ, this is the spin, in the spin language. You have the, okay, the XY part, which is a non-interacting part, if you want, interactions and disorder. And this, using Jordan-Wigner transformation, for example, can be seen as a fermions hopping, interacting in a random potential. Okay? So this is a quite general model, yet quite simple enough to capture the physics of MBL. And we are going to focus on this 2-point spin-spin correlation function. So these objects, of course, are known for a long time in condensed matter. They are very standard. And so what we generally expect for this problem to capture localization in a localized regime, because, okay, these objects should decay exponentially with some lengths, okay, correlation or localization lengths, as you want to call it. So this is what generally expected in the localized regime. In the delocalized regime, you will see it depends on the what we look at for this object. And there are 2 ways of looking at the correlation. One is like the bulk, like as a function of the separation between the 2 sides, okay? And another possibility is to look at something which has the maximal distance, okay? I will call it the system-wide, at distance L/2 across the chain. And so, and then if you do that, the nice thing is you can just scale your system size, okay? And you have only one length scale in your problem. So also the nice thing with this object is this is experimentally accessible. And there are a few MBL experiments, and in this experiment, they can measure at least the diagonal component, the CZZ, which in terms of fermions or bosons is just the density correlation function. And okay, there are some already preliminary experiments on very small chains, but they can access this object. And surprisingly, if you go to the huge literature on the theory paper about MBL, I could only find 3 where they study this correlation function. Okay, so we thought, okay, maybe we should try to do something on that. So let me try to explain first 2 simple limiting cases what we expect for this correlation function. So in the Anderson localization, which is at 0 interaction, delta equals to 0, this is an example of an exact diagonalization calculation in the middle of the spectrum, okay? So we are supposedly at infinite temperature. And so if you look at the XX or ZZ component of the correlation, you see this is a log, a linear scale. And so this is a beautiful exponential decay. From that, we can extract correlation lengths, psi. And so here I show how the correlation lengths in the non-interacting regime behave as a function of disorder strength. So you see they both are finite, and they only diverge at zero disorder as expected. So everything here is expected. And there is an interesting relation between the psi x and psi z. Okay, there is a factor of 2. I will not go into the detail. Yes, Satya. Oh, sorry. And in fact, also these correlation lengths are a good proxy for the localization lengths because the one particular localization length is put it here. So you see they behave basically similarly. Okay, so this regime is, in fact, is well understood. Now the other regime, the ergodic regime. Okay, so weak disorder or finite interaction. So here the ergodic regime can be basically a typical eigenstate is like a random vector in the Hilbert space, okay, of this form. So here this is a sum over all my basis states, okay, and all the coefficients can be random inside, but in magnitude they have basically the same order of magnitude, 1 over the Hilbert space size, okay. This is an important thing is the correlations in real space, they will not depend on the distance because I have a random vector. Okay, so there's no this notion of distance. So taking these two in fact, hypotheses for such random state, we will expect the XX correlation to be like this, 2 to the minus L over 2, which is in fact 1 over the square root of the Hilbert space dimension. And if you want the proof of that, this is like a one-line proof, in fact, because you can compute the S plus S minus on such a given state, and you see that you just flip a pair, and so you sandwich with the bra, and so what remains is a sum with random sign, which you pick up a square root of n divided by n, so that gives you the 1 over square root of n. But then if you look at the ZZ component, this is very different. Because here in our XXZ model, we have a conservation, which is the total spin conservation. And so the total spin conservation, that means this correlation, so the sum of this 2-point ZZ correlation function is a constant, and it can be 0. We can work in the subsector 0 magnetization. And taking the fact that, again, the correlation, they don't depend on this distance, all these objects, they are basically the same. And so you have a sum of L squared term, okay, and this one line, you find that this CZZ go like 1 over L, basically. So we have an algebraic versus exponential decay for the correlation. And this can be checked using like numerics on random state, and indeed, the ZZ goes like 1 over L, and the XX goes like exponentially. We can also check then for the true microscopic XXZ model, and this is also indeed what we find, of course, with a few corrections as compared to the exact random state, but still, we have this phenomenology where if you look at the XX correlation function, there is a finite correlation length, and if you look at the ZZ, there is formally an infinite correlation length because this is an algebraic decay. So of course, we expect something interesting to occur across the phase diagram. So this is a point, for example, here in the MBL regime, where we see that both components they decay exponentially with this hierarchy. It's not exactly a factor of 2 in that case, but there is still psi x, which is larger than psi z. And then if you go to, on the other side, a completely different decay of the correlation function, where psi x remain finite, but psi z is formally infinite. So further we expect an inversion of the dominant correlation across this line and something even more important to happen. And so here I show the correlation lengths, the psi x and the psi z, for such an horizontal cut across the MBL phase diagram. And so what you see first, you see indeed an inversion of the dominant correlation, but more importantly, what we observe, so the blue-green are the ZZ and the red are the XX. Here in this regime, we observe that psi z as a function of different system size, because we take different system size and we extract this local correlation length for increasing L, it's not stable. There is an instability. So the extracted correlation length increase with system size. So this is a sign of some kind of instability. And this is an example of the fit. So you can fit on the first system size, and then you can go to other system size, and we see that there is a drift. So this is clear in this regime. While in a regime where all the other estimates, they show a clear MBL behavior. Okay, so these are the standard estimate, and this is the extrapolation. So this gray line, this is the transition point extrapolated. Okay, so here we are in a regime where normally, if you look at the gap statistics, this is Poisson, without any doubt. While if you look at this correlation function at long distance, they show still some instability. And the instability is also observed beyond the point. Okay, here you see as a function of system size, the correlation is not fine, is not fixed. It's still growing a bit. So something is happening. And you can do that for all the scans, the possible scan. And so, okay, so it's a bit of French type color phase diagram. But we identify this regime of instability like all here, okay? So these are the extrapolated points that we already found with a standard estimate, and we have a regime of like quite large instability. So the next question is what this instability regime is. Is it what people call the pre-thermal regime? Does it catch resonances, avalanches? So we are going to try to answer that. So we keep along the Heisenberg line, okay? And we are going to focus on the distributions. Because so far I just show you the typical behavior. Let's look at the distribution of this correlation function. And so first, the bottom line here is the XX correlation function. And so for 4 different points along this line, we see that in fact, almost nothing is happening for the XX correlation function. There is no broadening, and the shape is basically the same, okay? So you cannot recognize there is a phase transition. But if you look at the ZZ, of course, this is very different. Because here, this is the ergodic regime, so there is sort of self-averaging behavior for this correlation. But then when you go to MBL or the instability regime, we have a correlation function when here different colors are for different system size. So with system size, there is a broadening. Okay, so, and the shape is very different from ergodic to MBL. And more importantly, if you look, for example, at this part of the distribution, this part are large correlations, okay? The largest possible. The largest possible is 1/4. And here it's log scale, so log 1/4, it's here. There are some rare events. And so we want to put our focus here on this rare event. And to do that, we make a very simple change of variable. Instead of looking at just log of C, we multiply by 4, okay? And you take the log. So if you do that, the big correlations means log of something close to 1, okay? So that means that this object in log scale will spread in a much larger regime. And so these are this large correlation regime here, okay, this gray area. And so using this simple change of variable, what we reveal here is a fat tail for this ZZ correlation function. And so these are rare events. And good thing is to compare to the XX correlation. Because the XX, this is on the right for the same disorder value. And here you see it's more like it's shrinking as you increase the system size, and there's no rare event. So the rare event are on the ZZ component. And to do that, okay, to explore more, we can say, okay, there should be a difference between typical and average. So let's do that. Let's compute typical correlation function, average, and look at how the correlation lengths, typical and average, behave. And they behave, of course, very differently. You see, for the XX, nothing really happened. But for the ZZ, so this is the ZZ correlation function that we have already seen before. But this is the average one. And you see, for the average one, the instability is even more visible for the average. And it also asks the question, but is this fit exponential decay? Is it a good description? Doesn't seem to be. So we try to do something else. And in fact, we found that in a broad regime, the average correlation is better fitted by your power law as compared to an exponential decay. So here I show some data. For example, on a semi-log scale, you see that only the strongest disorder is a straight line, which means apparently a good exponential decay, but all the other disorder strengths, which are like 7, 6, and so on, they are not well fitted by an exponential decay. And they are better, here log-log, fitted by some kind of power law, and we could also extract this power law exponent across the regime. So, in fact, this beautiful French phase diagram can be replaced probably better by this one, okay, which is, okay, the ergodic regime has not changed. We have this, this estimate for the transition. And what we have seen looking at this correlation function, that there is a regime, this green part, which has fat tail, okay, when you look at the correlation function. And only you need to go to larger disorder to say, yes, both and typical and average correlation, they decay exponentially. So this red regime looks more conventional MBL, while this one has something more. And these rare events, they seem to be power law distributed. They have order 1 ZZ correlation. And we are not looking at short distance correlation, we are looking at system-wide correlation in a background where typical correlation are very short range. So how this related to other works? So there is this very interesting one, different model. This is an Ising model, more like an Imbri model, for those you know, by Giulio Biroli, Hartmann, and Marco Tarzia, where, so the numbers don't compare, okay, because this is a different model, but they found that Wigner-Dyson statistics versus Poisson change around here. For us, it changed here, okay? Separate, in fact, the MBL, so there is an intermediate phase where there is a Poisson statistics, but some rare events. So this is a quite different way they use to look at this problem, but they found on the Hilbert space some rare path of possibly delocalization that proliferate and proliferate when you enter to the ergodic regime. So I think, yeah, our phase diagram kind of might agree, correspond to our fat tail regime, correspond to the rare path regime. And if you want to come back to the Morningstar phase diagram with all these landmarks, we don't have strong contradiction with them for the moment, and possibly what they call system-wide resonance, they find it around 7-8, that compares reasonably well with our estimate. But the avalanche type transition they have seen, we don't see that. So is that the end of the story? No, because in fact, you can even go to larger and larger disorder. And we have seen in very interesting stuff. So this is a simple sketch of what? Of the correlation function across the full spectrum. So what I did, I took 3 samples, and I did the full diagonalization, and you compute for all eigenstate the correlation function. And so you report this as a function of the energy density. So this is the ground state, this is the top state. So here, weak disorder, everything is the same, okay? So you have something which is delocalized. In the middle, 8, okay, you can see some strong fluctuations from sample to sample with some big correlation, but most of them are very small. But if you go to very large disorder, here I pick up 18, okay, so 18 is very large as compared to my phase diagram. And most of the sample, they show like flat. So flat is 0, and if I go to the log scale, this is how it is. So you see it's like 10 to the minus 4, the maximum. So this means exponential small correlation. But a few samples, this is what they show. Big peak. And you see this peak is at 0.245, very close to the maximal possible value of correlation. And this is weird because we are in a regime of disorder where everything should be like almost a product state. And we have found that, okay, let's go, maybe I should go a bit faster, but okay, so this is the same distribution I showed before, but for a larger broad of disorder strength from 2 to 20. And so you see the fat tail regime start to arrive at 4, 6, 8, but it seems to continue and at some point will disappear. But how to do better? So to do better, we say, okay, let's try to integrate a part of this distribution to kind of estimate the probability to observe a rare event of strong correlation. Okay, so this is this weight W star. Okay, so here I pick up a cutoff at 0.1, but that can be 0.2, 0.15. This is not really important, this value. Okay, so this is just the integral of the largest part of the correlation. And this can be fitted as an exponential decay, and the important thing is to compare that to the size of the Hilbert space. So I take this W star and I multiply by the size of the Hilbert space, so that gives me how many events I have in a sample. And you see that these keep increasing here, so different colors are for increasing system size. So in this broad regime, up to a disorder of about 20, these rare events are present, and their number is not increasing linearly with the Hilbert space size, but it's increasing with an exponent. Okay, so we are not yet related to some other exponent of the problem, but an exponent which is between 0 and 1, this D exponent. And this is another way of seeing it. This length lambda Z is very big here in this green regime, and it decays, and it only crosses 1 over log 2, which corresponds to the Hilbert space dimension. Hilbert space dimension is 2 to the L, around this disorder 20. So looking at this kind of object, we kind of identify 3 regimes. One, which is our fat tail regime as before, okay, where this psi effective grows with system size, and this is what we kind of see here for different system size. Another regime, the yellow one, where there's no size dependence, but this length is still above a threshold, and the orange one, where now rare events are super rare. So in fact, you pick up a sample, you don't see it. And from time to time, you can see that. And this is also confirmed by looking at the maximal correlation per sample over eigenstate. You take a sample, you get the exponential eigenstate, and you pick up the maximal correlation. Okay, and you do the statistic on that. And this gives you exactly the same crossing point at disorder 20. Okay, so I should speed up, sorry. So our scenario is the following. So we have this, the blue regime, this is the ergodic phase. We have this rare event regime that we have first identified, and then we just discovered that the rare event can still be present here, but they become more and more rare, up to a point of about 20 in the disorder strength, where there's no rare event. Okay, maybe 1 minute of bonus. Because, we could ask, what are these special eigenstates? Why at disorder 20, I can have like all the correlations which are 0, 0, and some 1. And so let's go there, for example, and this is what we have identified. They come by pair. They come by pair, and they are almost degenerate, okay, and they have almost the same value for the correlation. And so what we have just identified is they are like cat states. They come by pair, and there are a few body resonances. So here I try to sketch, this is not the exact form of the ground state, but this is very close to that, in fact. If you look at them like in the computer, this is what you find, and this is what it looks like a bit. It's not like a singlet, of course. This is like a pair state, like a Bell state, if you want, involving only 4 spins. And all the other guys, the black guys, are frozen. Okay, so these resonances are just touching a few sites. And if you go in the spectrum, this is how they look like. They are almost degenerate, and they are always neighbors in the spectrum. And their individual cat gap is below the natural gap of the spectrum. Okay, so I'm done. So this is the conclusion. So I hope I showed you that this MBL phase diagram is richer than what we previously thought. We have identified, using this correlation function, a new regime of rare event where long-distance spins can get strongly entangled in an otherwise very localized background. And this rare event can, in some regime, dominate the average. Regarding this cat state, so this is a work in progress now with Fabien and Jeanne. So we want to understand how they proliferate and how they connect to the instability, various instability in the problem. Are they like the seed of the ergodic transition or not? Okay, so this we'll see. Thank you.
Thank you, Nicolas. further questions?
Hi, just so in the green region, you said that the spectral statistics is Poisson. So by that, do you mean even all sorts of spectral statistics, like spectral form? The spectral form factor does not have a ramp, and so it is completely.
The spectral form factor, we have not computed it. I know that this was a subject of controversy, but yeah, we don't have we have not computed it, so I cannot say for this regime.
Okay, okay.
But in fact, the spectral form factor has some more technicalities and more like ways of computing, some filtering effect and stuff. So I think there are a few things under the carpet in a few papers that were published on this object.
Okay, and just one more question: this green region having Poisson statistics, but power law correlations. Is it do you think it's quite a generic statement, not really specific for the Heisenberg line, I mean, let's say quasi-periodic, flow KMBL, I mean, all sorts of, I mean, is it a very universal?
I cannot tell for the moment. What I see, if I compare to Giulio's and Marco work, they also have an intermediate regime for a completely different model with no symmetry. Their model has no symmetry, so easing with mixed field. And for us, of course, there is this conservation of the total spin, which might play some role, I guess. Okay. Then for the quasi-periodic, I don't know, because most of the people they say, oh, this is because Griffith's effect, rare event in the configuration of the disorder. But here this is random disorder, so there might be some Griffith's effect. But why, if you take like a random configuration and you take like an exponential number of eigenstates, only a few of them, although they have the same disorder configuration, all the guys, but only a few of them show this very particular response. So there might be some other thing as just the configuration in real space. So that means for the quasi-periodic, it might be that we also observe that.
Okay, yeah, thanks.
Yeah, so I have a very naive question about, like you said that the exponentially decaying correlation I can see depends on what the quantity you look at. Like, for example, in one phase, in the XX core 2-point correlation was, I mean, the ZZ correlation was the one which actually shows that it is the exponentially decaying in the MBL phase, but not in the other phase, right? So my question is about, is there any understanding whether which one is to look at for a given Hamiltonian depending on the symmetries?
That's a good point. Okay, for us, in fact, the fact that you have this sum of SZ, which is a constant number, you can understand that the ZZ correlation is your guy. Otherwise, I don't know. There's no simple answer.
Okay. And I have another also one, probably one naive question, like in your Hamiltonian, you have put a random field along the Z direction, right? So from a perspective of, I mean, equilibrium phase transition viewpoint, I have already broken the symmetry along the Z direction, right?
Sorry?
Of the Hamiltonian.
In the symmetry of?
Symmetries, I mean, SZ, because Z2 symmetry is broken in the Z2 symmetry is broken in the Z direction, right? So why I am looking at SZ then as a order parameter?
Here we don't have a Z2 symmetry. No, here this is a U1 symmetry. Okay. No, because the field in the Z is in the Z direction, so you cannot flip all. If you flip all your spins, this is not the same state if you want. Okay. There's no Z2 symmetry. There are models with Z2 symmetry.
Oh, so because you have a random field and this is between minus H to H, that's why the Z2 symmetry is not broken, you are trying to say? Or
there's no Z2 symmetry of the
Okay, thank you.
Okay, so you should. Let's take the last question and then we continue
Okay,
during the
very
coffee
quick.
break.
But do you expect the same phenomenology to appear in inverse participation ratio? Because this inverse participation ratio is related to Z-Z correlation, right, somehow?
Okay, first of all, the participation ratio depends on the basis where you compute it.
Yeah, let's do it on Z.
So let's do it on
computational
Z,
level.
right? And, well, it's not that, for one problem with the participation ratio, it's a more global quantity. So for example, if you're interested in this cat state, you could say, cat state, they should show up as a log 2 in the participation, right? Because 1 over square root 2, so it will give you like this. But the problem is, this log 2 will be hidden in the big background because the participation entropy or ratio integrate, in fact, all the sites, all the states. And so, because of course, this cat state is not as simple as it. Okay, there are some fluctuations around it. And so, because, yeah, we have worked a lot on the participation entropy with Fabien during the past years, and we have never seen, and we also did simulations at very strong disorder. And at very strong disorder, participation entropy is very
Just
small.
for the states.
It's very small, and nothing is visible there. So it doesn't seem to capture the rare events as this guy does.
Okay, so we will continue during the coffee break. So let's thank Nicolas and all the speakers of this session.